In this video, I will be explaining quantum gates and those quantum gates that take one input or the single input. So if you are the beginners in the quantum computing, you maybe get surprised by knowing the fact that quantum gates are matrices. If you have some digital electronic backgrounds, you may think that a gate is an electronic circuit that takes some input, like for example, a NOT gate, which takes a single input and that transforms it into the output. If the input is the 0 for a NOT gate, the output is the 1. In the same way, quantum gates also transforms input into the output. But unlike the electronic circuits, in the quantum computing, we treat quantum gates as a matrices, and they are specific matrices which we call it as unitary matrices, and they possesses some properties. For example, the unitary matrix means that a matrix, if we take the conjugate transpose of that matrix, a conjugate transpose means that the elements, the the elements which are the complex numbers that are converted first into the its complex conjugate, and then we take its transpose. If we are performing these two operations together, we call it as the complex conjugate. And if we multiply the matrix and with respect to its complex conjugate, we get an identity matrix. Identity matrix means a matrix in which all the elements that are present in the diagonal are of are having values 1. So those matrices are called as the unitary or the identity matrix. And the unitary matrix is the matrix. If we take the complex conjugate first and then we multiply the complex conjugate of the matrix and the matrix itself, we will get a identity matrix. And this operation is a commutative operation, means that u times u plus and is equal to the same u plus multiplied by the u. So these are the commutative operation. A unitary matrix. So all the quantum gates are basically the unitary matrix. Some of the quantum gates, not all, some of the quantum gates are the Hermitian matrix. And Hermitian matrix is a matrix. If we take the complex conjugate of the matrix, then the complex conjugate of the matrix and the matrix are both the same. So that's why those matrices are called as Hermitian matrix. If the matrix possesses this property, means the complex conjugate of the matrix and the matrix are the same, then that type of matrices are called as the Hermitian matrix. For a matrix that is both unitary and Hermitian, so its inverse and the matrix are the same. Or if we multiply the inverse of the matrix and the matrix itself, we again get an identity matrix. Such matrices are called are reversible quantum gates. Means that if we apply the from the output, we can get the same input. So let us take one example to understand the properties of the unitary properties of the matrices that makes them the quantum gate. So here I am taking one example of a matrix in which the row, it is a 2 by 2 matrix, 2 rows and 2 columns. The first row has 0, minus I, and the second row has the elements I and 0. So this is a matrix which consists of complex numbers also. So if I take the complex conjugate of this matrix, suppose that for example I am taking the first column and making it as the row of this matrix, so I will get 0, and because the second element in the column is the I need to take its complex conjugate, so that's become the minus I. And now I am taking the second column, and then making it as the second row of the matrix. So the first element is the minus I, so I will make it as the I and 0. So this matrix and the original matrix is the same. So the complex conjugate of the matrix and the matrix are the same. And if the complex conjugate and the matrix are the same, that types of matrices are called as the Hermitian matrix. So this is an example of a Hermitian matrix. Now let us multiply the y and the its a complex conjugate now. So here I have written the y, this is y, and this is the y complex conjugate. Basically, both are the same. And I am taking the multiplication of these two matrices. So let us multiply first row with the first column. Then I will get 0 multiplied by 0, this, and minus I multiplied by minus I. So this is the first term. Now let us calculate the second term by taking the first row and second column. So I am now multiplying the first row and second column. So this term becomes 0 multiplied by minus I, and minus I multiplied by 0. So this term becomes, now let us calculate the second row with the first column. Now what I will get is that I multiplied by 0 times 0 multiplied by I. So I multiplied by 0 plus 0 multiplied by I. Now let us take the second row and second row second row and the second column to get calculate the element 2 by 2 or 2 comma 2. So I multiplied by I minus and 0 multiplied by 0. So if I calculate these terms, the first term will becomes 1, then a second term will become 0, and I multiplied by 0 and 0 multiplied by I becomes 0, and I times I becomes 1. See, try to understand the minus I multiplied by I, how it is calculated. This becomes the, which is equal to minus I square, and minus I square means that which is equal to minus and minus 1 square, sorry, minus 1, so it becomes the 1. So now this matrix is the identity matrix having the 1 are present at the diagonal position. So this is a identity matrix. If we multiply y and its with its complex conjugate, and then we get a identity matrix, that matrix is called as a unitary matrix. So this is an example of a unitary matrix. Now this matrix, that is the Y matrix, is a both unitary and Hermitian matrix. So such matrices are called as the quantum gates. Now we are going to take examples of the quantum gates. Now the first quantum example of a quantum gate is a Pauli X gate. So Pauli X gate is, as all the quantum gates are unitary and some of the quantum gates are the Hermitian. This Pauli X gate is an example of a example of a quantum gate which is both unitary and the Hermitian matrix. So this is the symbol for the unitary X gate. It takes the one input and it converts the input into the output. So this is the symbol for the Pauli X gate. And the matrix that is corresponding to the Pauli X gate has is a 2 by 2 matrix, and the first row of this matrix has the element 0 and 1, and second row of this matrix has 1 and 0 as its elements. When we will discuss all types of single input matrices, we will observe that all single input quantum gates are basically 2 by 2 matrices. So the working of this matrix is like this. If the input is the gate 0, the output is gate 1. If the input is the gate 1, then the output is the 0. These are the pure state. If the input is the gate 0 and gate 1 are the quantum state, which we call it as the pure state. If the input is a superimposed state, like for example, alpha times gate 0 plus beta times Kate 1, then and we are apply this input to the Pauli X gate, we will how it will work is like this. The X operation is a linear operation over the addition. Linear operation over the addition. It means that linear operation over addition, it means that we can apply x individually on the terms that we are going to add. So we are going to add this alpha kate 0 and beta kate 1. So we can apply separately x on alpha times kate 0 and beta times kate 1. So if we apply uh, gate 0 on the x x gate, what we will get is the 1. And if we apply x gate 1 as input to the x gate, what we will get is the 0 as its output. And if we observe this, that uh, if the input is a superimposed state for a quantum Pauli X gate, the coefficient of gate 1 and gate 0 are interchanged or the swap. Earlier, alpha was the coefficient for gate 0, but now it is the coefficient of gate 1, and beta was the coefficient of gate 1. Now it has the coefficient of gate 0. So in this way, a superimposed state is converted or transformed by the Pauli X gate. So let us try to see how the Pauli X gate is applied by seeing the um, matrix multiplication. See, this is the we are here. What we are going to apply the Pauli X gate on a superimposed state like alpha times state 0 plus beta times state 1. So on the superimposed state, we are applying Pauli X operation. So if we apply this X operation on the Pauli X gate, the matrix corresponding to the Pauli X gate is this, where the first column will have the element 0, 1, and the second column will have the element 1, 0. So this is the matrix for the Pauli X gate. And this is the vector representation of the superimposed state at which the alpha is the coefficient of the gate 0. That's why we have written alpha at the 0th position, and beta is the coefficient of gate 1, so we have written it at the 1 position. And if we multiply these two matrices, if we take the multiplication of these two matrices, what we will get is that a second matrix. So here we will take the matrix multiplication of the Pauli X and superimpose the state by first taking the first row, and we are multiplying with this column. So if we multiply, so this is the multiplication is like this: 0 multiplied by alpha and 1 multiplied by beta. So this is our first term of the resultant matrix. And in the to get the second term in the resultant matrix, what we are going to do is that one we are taking the second row and multiplying with the second matrix, all the terms from the second matrix. So we will get 1 times alpha and 0 times beta. Let us try to simplify this. So 0 multiplied by alpha becomes 0, and 1 multiplied by beta becomes beta, and 1 multiplied by alpha becomes alpha, and 0 multiplied by beta becomes 0. So this is the beta and alpha, which is nothing but this is the Kate notation for this column vector. Beta is present at the 0th position. So that's why we have written beta times Kate 0, and alpha is present at the 1 position. That's why we have written it as the alpha times Kate 1. So in this way, we can see how the Pauli X gate matrix converts the superimposed state into the other state. Similarly, you can find out how it converts the pure state of 0 and alpha by multiplying. Suppose that if you want to calculate transformation of Kate 0, so the Kate 0 will have the first element as the 1. So the first element will have 1, 0. This is the representation for Kate 0, and multiply this matrix with our Pauli X 0, 1, 1, 0, and you will get a resultant matrix which is nothing but which will be equal to 0, 1. And if we multiply this matrix 0, 1, 1, 0 with Kate 1, 0, 1, and we will get 1, 0. So this is the way in which the different inputs are converted by the Pauli X gate. So this is all about the first type of single input gate, which we are calling it as the Pauli X gate. Thank you.